how would we find the potential energy of two charged particles near each other? Wait, why would there even be potential energy if there's two charged particles near each other? Well, it's not too hard to see. If we have one positive charge and another positive charge, remember, we know that the potential energy equals QED, right? Where D would be the distance between these two. Okay? So this particle here creates an electric field that this particle is inside of, right? And so if this particle is in an electric field, it is going to have a potential energy, okay? And it turns out that that potential energy, so specifically, so this is always true, right? But specifically for the case of 2-point charges, you would say that there is a potential energy in this system equal to K Q1 Q2 over R. Okay, so if this is Q1 and this is Q2, and the distance between them is actually R, then we would say that this is the potential energy stored in this system of two charges. Okay, so that if we decided to let this charge go and fly off to infinity because it wants to, because it's close to another positive charge. If this guy wants to fly off, all right, then we can use conservation of energy using this formula to be able to find out what that velocity will be when the charge is way off elsewhere, which is kind of neat. Let's do an example of this. Okay, so on the same slide, it says a proton is fired from very far away. That's physics language for infinity away, okay? And it's fired away at a 1 millimeter diameter glass sphere with a charge of 1 nanocoulombs. What initial speed must a proton have just to reach the surface of the glass? Okay, so we can look at this again as a conservation of energy problem. E1 equals E2, okay? So in the E1 situation, okay, so this is our E1 situation. We have a proton, so positive, going towards this little glass sphere with radius r. Okay, and we know that as it gets closer and closer, because these repel each other, right? It's going to slow down, slow down, slow down, slow down, slow down, slow down. It's almost like if you throw a ball up in the air, it slows down, slows down, slows down, slows down, and then accelerates the other way. This would slow down, slow down, slow down, slow down, and then start to accelerate back the other way. All right? And so the question is, what must be the velocity here that you shoot this electron at? Okay? What must be that velocity so that it just reaches here at this point? And if it just reaches here, we know that that final velocity, so that's v1, that final velocity must be 0. Okay, so our E2 then would be when this particle just made it to the edge and then it's going to start accelerating back the other way because that's what forces do. It'll repel and push it the other way. All right, so what is our initial potential energy? Well, we know that the proton is being shot at this positively charged glass sphere, right? So if it's being shot, there must be some kinetic energy there. So we're going to say KE1. Right? But here's the thing. At infinity away, right? If this is shot from very, very far away, in other words, infinity, that means R is really big. R is basically infinity. If you have an infinity denominator, what is U? U actually, and so, by the way, U is just another way of saying potential energy. These are used interchangeably in physics, U and potential energy. So if it's more comfortable for you, I'll try to keep using PE there. Okay, so our PE1 has to be 0 because it's from very far away, which means really big R. Really big R means that that goes to 0. So we can just say that's 0, right? And so what about E2 when it just reaches the glass sphere? Okay, well at that point we know that V is 0, so there's no more kinetic energy anymore, right? But at the same time, R is getting really, really small. If R gets small, the potential energy goes crazy up. So that'll mean that the potential energy there is awfully big. Yeah. So basically, this becomes a problem of the initial kinetic energy must equal the final potential energy. All right. Well, what is the initial kinetic energy? Obviously, it's 1/2 mv squared, right? And what is the potential energy? Well, we get that from this formula, K Q1 Q2 over R. I'm sad to say that there's nothing here that cancels. Normally in conservation of energy problems, you get to cancel stuff out. That does not happen here. What are we going to do? So we go ahead, if we take the difficult step of putting in all those values. So we have 1/2 times the mass, it's a proton, so that's going to be 1.67 times 10 to the minus 27. We're solving for V. We want to know that minimum V required so that it just makes it to the other side. So that's V squared, what we're solving for. K is 9 times 10 to the 9. Q1, I hope I'm not running out of space too bad here. Q1, so Q1 is the proton. Charge is 1.6 times 10 to the minus 19, right? Q2 is the charge of the glass sphere, which is 100 nanocoulombs. So that's times, if I'm getting out of the frame, I'm sorry, but I'll verbally say it aloud so that it's clear. So it's 9 times 10 to the 9 times 1.6 times 10 to the minus 19 times 100 nanocoulombs, which is 100 times 10 to the minus 9. And then you have R is this final distance. How far is it away at the end? Well, that's just the radius of the glass sphere. It's a 1 millimeter diameter glass sphere, so that means you're dividing by, very out of space. It means you're dividing by, in this case, 0.005, right, which is the radius. If it's a 1 millimeter, then it's a 0.005 meter radius. So it's this stuff divided by 0.005. It's a little bit of a mess. Go ahead and solve for V, right? I get it. You've all seen worse before, right? Putting all this in, multiplying by 2, dividing by 1.67 times 10 to the minus 12, taking the square root, I get a velocity of 4.2 times 10 to the 5. Again, does not violate Einstein's theory of relativity. It's under the speed of light. We're good. So we have to shoot that proton at a minimum of this speed so that it just makes it to the edge. Cool. We made a prediction about the future. We're going to do one more problem in this video, and that is looking at the case of what do you do if you have multiple particles, okay? And the answer is you just sum up the potential energies. And the good news is potential energy is not a vector. Energy is not a vector. So when you sum up the energies, the potential energies, due to several particles together, you don't have to worry about sines and cosines and breaking up things into components. You just add it. So it's one potential energy for every particle that you add. So in this example, we have 3 electrons lined up like this. Okay, and at some point after, you like kind of pop it, right? And so this is before, and then the after over here is you still have that electron and that electron, but this electron goes firing off at some velocity. Okay, so question 1 is this center electron at a point of stable or unstable equilibrium? Okay, a stable equilibrium would mean that if you hit something a little bit, it goes back to the equilibrium point. Like, so a stable equilibrium would be like for a ball. I have a ball. If I hit the ball this way, it rolls back down. If I hit the ball this way, it rolls back down, right? An unstable equilibrium is like this, where if I have a ball here, if I hit it this way, it just keeps going, right? If I hit it this way, it just keeps going. Stable, unstable. What about this case? Okay. Well, if I hit this even a little bit, then if the electron's over there, so right now it's perfectly balanced between these 2 negative charges. But if I bring this guy over here, then this charge will be repelled by this charge and repelled by this charge, so there will be a net force in this direction that is unstable. If I just hit this a little bit, it wants to shoot away on and on and on and on and on, away forever. Okay, so we got that part. That's easy. That's easy. The other question, though, is, what is going to be the speed of this electron all the way off at infinity, right? So it's trying to get away from these two particles, and it goes away, and it's going to have some velocity. What is that velocity? Bottom line is, we can use conservation of energy to solve that problem, okay? So we just say E1 equals E2. Well, what is E1? E1 is the potential energy of both of these interactions. So that's all this potential energy, right? And that's got to equal to the kinetic energy that this charge gets when it goes off into infinity. So that's going to be kinetic energy. Well, what is the potential energy here? Well, you have two interactions, right? You have this one and you have this one. All right. The first one is going to be K Q1 Q2 over R. The second one will also be K Q1 Q2 over R, right? You have the potential energy due to these and the potential energy due to these. So that's the total potential energy that this charge has at the beginning. And that's got to equal 1/2 mv squared when the charge has flown all the way off, right? This is basically just 2 times K Q1 Q2 over R. We've been told that these are both electrons, so we know the charge is 1.6 times 10 to the minus 19. Okay, so basically all we have to do is say 2 times 9 times 10 to the 9 times 1.6 times 10 to the minus 19 squared, because these two charges are the same, all divided by the distance between them. It tells us here the distance between them is 1 millimeter, so that's just 0.001 meters. Okay, so all this potential energy turns into kinetic energy over here. We just need to put in, for M, 9.1 times 10 to the minus 31 kilograms. And then we solve for V. And that V, if we multiply everything, multiply by 2, divide by the mass, take a square root, we get a velocity of, I get 1,006 meters per second. Cool. Check me if I'm wrong. Felt like 2 really intense first videos for this week. But to summarize, all we've done is found the potential energy as a result of point charges. Okay? And we said that that potential energy adds. For every particle that you add to it, you have to add another term of potential energy. So if it was just these two, then we can take away one of these. But now that there's a potential energy interaction here, we have to add another one. We set that equal to the kinetic energy when you hit this and it goes all the way off to the side, because all this potential energy stored in this, right? It's like this, like a ball on top of the hill, or like, you know, when you have elastic that's pulled, it's kind of tense. So when you release it, it snaps away, and all the energy stored has to turn into the kinetic energy at the end. And that kinetic energy will result in a velocity of 1,006 meters per second. All right.